Okay, in this video I'm going to do problem 1 of homework 5, and in this problem it says that we need to prove the statement if true, otherwise find a counterexample. And it's about the subject of adding even and odd numbers and whether or not the sum is even or odd. And it says for part A it says for all natural numbers x and y, x plus y is odd if one of x and y is even and the other is odd. For part B, it sounds very similar. For all natural numbers x and y, if x plus y is odd, then one of x and y is even and the other is odd. Okay? They're both true, and I'm going to make a little chart here that shows what happens when we add even and odd numbers. Okay? And I'm going to add an even to an even, and if I add an even plus an even, I'm going to get another even. If I add an even to an odd, I'm going to get an odd. If I add an odd to an even, I'm going to get an odd, and if I add two odds, I'm going to get an even. Okay? So this is a little chart that shows sort of the complete situation as far as adding even and odd numbers. And basically what I'm going to do is I'm going to say let's let P be the statement x plus y is odd. And then Q will be the statement one of x and y is even and the other is odd. So let's just call this P and this Q. Okay? And I'm going to call Q, we have one of each. Okay? And you know what I'm talking about. One of them is even, the other is odd. Okay? Then part A is a statement that P if Q. And part B, so you got to watch out here, because what this really means is it means if Q, then P. That's what part A says. Part B is a straight out if P, then Q. Okay? So in words, it's if P, then Q, and it is in symbols, if P, then Q, like this. In other words, they're both true, and we need to prove both of them, and what it's really saying is that P, if and only if Q. Okay? When we've got the arrow both directions, we have to prove it both ways. So I'm going to do part A first, and I need to prove if Q, then P. And I'm going to do this one. Q is the statement that we have one of each. So I'm going to do this one as a direct proof. I'm going to assume Q and show that P follows. Okay? And let me give myself a little bit more room here. Q says that we have one of each, and I'm going to let x be even and y be odd. Okay, I don't have to consider the reverse situation because x and y are dummy variables, and I could have just reversed them, their names. Okay, if x is even, now here's the step. I'm going to say there exists some integer a such that x is 2a, and because y is odd, I'm going to say there exists an integer b such that y is 2b plus 1. So this is the form of an even integer twice another integer, and an odd integer is twice another integer plus 1. Okay? Then what I can do is I can say then x plus y is equal to 2a plus 2b plus 1. And I'll simply factor out a 2 from the a plus b, and I'm left with a plus 1. So this is of the form 2 times an integer plus 1. And that means that it's odd because it's of that form. Hence, x plus y is odd, and hence we are done because that's what the statement P was in the first place, that x plus y is odd. Okay? For part B, it looks like I might have room to do it right here. I'm going to prove the opposite. If P, then Q. It turns out that it's a little bit difficult to start with the statement that x plus y is odd and to prove that one of them, we must have one of each. Okay? And instead, and I think I went over this in class at least once, what we're going to do is we're going to prove the contrapositive. That is, if not Q, then not P. Okay? So we assume not Q, and we show not P. Okay? So not Q means we don't have one of each. Well, if we look at our possibilities, we've got 4 possibilities. Either they're both even. We've actually sort of got 3 possibilities. Either they're both even, or they're both odd, or we have one of each. Okay? And so if we're assuming that we don't have one of each, then there are 2 other possibilities remaining. Okay? Assume we don't have one of each. Then we have 2 cases. First case is that both are even, and the second case is that both are odd. Okay? And I'll take one after the other and prove them. So case X and Y are both even. And you're going to see what I do is simply repeat this business of coming up with the A and the B and adding the 2 together and showing that it all works out. Then there exists an A that's an integer such that x is 2a, and there exists a b which is an integer such that y is 2b. Hence x plus y is 2a plus 2b, which is twice a plus b. Hey, this is very similar to the previous one, which is 2 times an integer, and hence x plus y is even, and hence x plus y is not odd. And that's exactly what we were trying to prove, because we're trying to show not P. And P was the statement that x plus y is odd. Okay, so we were trying to show that x plus y was not odd, and in fact, if we showed that it's even, that shows that it's not odd. Okay. Now I'm going to take up the case where they're both odd. Okay. So here's case 1. Here's case 2. I'll give myself a little bit more room here. It's the case they're both odd, right? Yep. Both x and y odd. And you'll see I'm going to do basically the same thing again. Then there exists an a, which is an integer such that x is equal to 2a plus 1, and there exists a b, which is an integer such that y is 2b plus 1. Hence, x plus y is 2a plus 1 plus 2b plus 1, which is twice a plus b plus 1, which is of the form 2 times an integer, and hence x plus y is even, and hence x plus y is not odd. Okay, this does it. I believe what I was doing here in case 2 is essentially, well, it's a little bit different from what I did over here in part A. In any case, I've done it, I've proven it in both cases, and we have shown in this problem that P, if and only if Q, that is, that the sum of two integers is odd if and only if we have one of each, even and odd. Hope that helps.